Converting to standard form. When you've got a big number like this, obviously you want to write it in a more economical way. So standard form works on the principle of place value. What is the value of the first digit in a number that doesn't have any decimal points? It's the units, and then the tens, and then the hundreds, and then the thousands, and so on. You know all this. But it's because our number system is decimal. We have 10 digits. When you get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you run out of numbers, and so you have to use another digit to signify 10, and then up to 99, 100, and so on. So effectively, these are powers of 10 that we're using here. Tens are here, those are 10 to the 1, so it actually starts on 10 to the 0. Anything to the power 0 is 1. Units are 10 to the 0, just accept it. Those are 10, 10 to the 1, 10 to the 2, you know 1,000 is 10 to the 3, 4, 5, a million is 10 to the 6, 7, 8, 1,000 million, a billion is 10 to the 9. So this place value here is 10 to the 10. So in an 11-digit number, I've just written 11, sorry. Oh, and it's off the screen, that's helpful. Sorry. So in an 11-digit number like this, the front digit is going to be 10 to the 10. So this is saying that we have 7 10 to the 10s, but we've also got this 1 here. So instead of being 7 lots of 10 to the 10s, it's 7.01 10 to the 10s. A good anchoring thing is just to think of these key values. That's thousands, that's millions, that's billions, and so on. And those always go up in 10 to the 3s. But yes, that is 7.01 times 10 to the 10. When you've got numbers which are less than 1, i.e. they start 0.00 something, it does work on the place value system, but you have a handy trick. Count the number of zeros at the start of the number, including the one from the decimal point. There's 6, so we know it's going to be times 10 to the minus 6. And then just do the first one dot the other one's 4.157. That's your answer. You can justify it with place value as well, but hey, there's a little shortcut. 7.01 times 10 to the 3, remember that 10 to the 3 is thousands, so 7,000 will be 7,000, 7.01 thousands will be 7,010. 2.5 times 10 to the minus 7, again we can use that zeros trick. We're going to do 1, 2, 3, 4, 5, 6, 7 zeros, and then write the 25. This you type into your calculator. We do switch it on first of all, and you do 1.2 times 10 to the power, that's this button here, it's sometimes exp on, oh, can't see it, times 10 to the x here, that, if I delete, so you can see that again, so, right, 1.2 times 10 to the power x, this is exp on some calculators, and in this case 4, plus 7.1 times 10 to the 5 equals, and it's giving me the answer as a normal number, which is what we wanted anyway, so it's 722,000. It then asks for the next one in standard form, which is 2.3 times 10 to the minus 3 divided by 8.4 times 10 to the 8, and it gives the answer in standard form. I wouldn't bother writing the whole thing. I'd cut it off to 3 significant figures as standard, so 2.74 times 10 to the minus 12. I remember the number 2.74, you can still see it on the screen. Right, that's a 7 by the way. Now onto the areas. Oh dear, people forgot their areas. These are fairly simple rules, so let's just make sure we know them. Triangles half the base times the height, not just base times height. So we do 8 times 16 and halve it, which of course is 64. Area of parallelogram is base times height. That's not the height. Okay, that can be whatever length you like. A parallelogram which looks like this, if it is a parallelogram, has exactly the same area as this one because it's got the same base and the same height. And so it's just 9 times 12. Height, not the slant height. So 108. This last one, lots of complicated ways of doing this. The easy way is by the old song. Half the sum of the parallel sides times the distance between them. That's the way that you will find the area of a trapezium. Beautiful singing, obviously. So half the sum of the parallel sides